Why did I decide to automate? Well, like most small manufacturers, we assembled and packaged more or less by hand. It was a very manual process that was dependent on labor. Once our business gained some traction, however, our labor dependency became a real problem. Explain that?
Yes.
Well, at this stage in our business, order flow was really unpredictable. We couldn't afford to build a warehouse full of inventory and hope we'd sell it. So when big orders did come, we had to assemble, package, and deliver on really short notice, and that required labor. And in our experience, good workers don't sit around waiting for unpredictable short-term engagements. So it was the business risk of not finding quality labor when I needed it that really drove the decision more than the potential for cost savings. What you're really asking is, why would I ever decide to design and build our automation machinery myself rather than hire a specialized engineering firm on the outside? It's a good question, and the short answer is necessity. Our project just seemed way too small for that kind of muscle, and secondly, most importantly, we just didn't have the capital. So that's why we did it. Besides, I knew I could do it. I just had a few things to learn, like mechanical engineering, robotics, and electronics.
These are made of plastic.
That's true. Most automation machinery is machine tooled out of steel and aluminum. But that's very expensive and mistakes are costly. I knew we couldn't afford that, so understanding the advances in 3D printing, I had the idea of simply 3D printing my machines out of a durable hybrid plastic. If I made mistakes or subsequently came up with improvements in design, I could simply redesign it and reprint it.
So where do you start?
I guess I started by defining the tasks required to transform all of the product and packaging components into finished products. So you know, we make a do-it-yourself product I invented called Fix-A-Latch. Anyway, I then arranged those tasks in a logical, sequential order, which should come first, which should come second and third, and so on. In the next step, I took each one of these tasks and sketched out various machines that could accomplish that task. I'd usually sketch several designs for the same task, and from that I would pick what I thought was the best. Once I thought I had the optimal design, I built a digital 3D model of what I'd drawn in CAD. I then printed and assembled the parts. Our assembly process is built along a straight track. It starts with a magazine of blank bases. A plunger slides beneath the magazine and loads one blank base onto a beveled track. As these bases are pushed along, they pause beneath a taping applicator mounted on a sliding gantry. Two lasers recognize breaks between the tape segments and inform the rollers when to advance and when to stop. Once taped, bases are pushed along into a flipper that rolls the base onto its back. A spear ascends up through the latch hole in the base, while a linear actuator then pushes the base forward onto a second track. As these bases advance down the track, they pause beneath the adhesive applicator. Here, adhesive is fed from a pressure pot through a diaphragm valve and eventually through 5 dispensing needles to the face of the base. The next machine extracts a strike plate from a magazine and pushes it out over the pre-glued base. A spear ascends up through the latch hole in the base to guide the strike plate into place. The spear then descends out of the way and the bases advance along the track. At the next stop, a label applicator dispenses a triangular label onto the face of the base. A laser communicates the position of the label roll to the motherboard. The fully assembled and labeled unit is then fed beneath an upside-down conveyor. This does two things. First, it applies pressure while the adhesive sets, and secondly, it takes over and pulls the base forward along the track. As the unit exits the conveyor, the adhesive is set, and the units are pushed out and onto a long spear. Once full, these spears are switched out and taken to the packaging line. The packaging process is built around a circular course with 24 cars. Each car is loaded with a clear plastic blister. These blisters are preformed to hold 2 units and 4 installation screws. Once loaded, the operator hits the start button and the cars begin to rotate. Each car will make 24 precision stops per rotation. These stops are controlled by a laser that shoots down onto the cars as they pass. The first stop on the course is an elevated hopper filled with short screws. When a car stops beneath it, a disc in the hopper begins to rotate. As it does, cutouts in the disc catch single screws and separate them from the others. When screws reach the top of the hopper, they drop through the bottom into a chute. A proximity switch on the bottom of the chute detects the metal as it passes and communicates this to the motherboard. Screws funnel into a hose, then shoot down around and into the dispenser where they drop into the screw compartment in the blister. At the next station, a second hopper dispenses 2 longer screws. But to make sure there's room in the blister compartment for these screws, the blister passes a blower that pushes the small screws to the far end of the compartment with a puff of air. Since the second hopper dispenses large screws, the cutouts in the disc are longer. But otherwise, the hoppers work the same way. Screws are picked up, dropped, and dispensed into the blister at the bottom. With all 4 screws loaded, cars advance to the next station where finished units from the assembly table are loaded. When the car is in position, a plunger slides the bottom unit from the magazine and onto the mounting deck. Once on deck, a second plunger pushes the finished unit into the blister. Just to make sure the unit fits all the way down into the blister, a drawbridge-like arm presses the unit into place. At the next stop, we load the second unit. It works the same way. A plunger pushes the bottom unit onto the loading deck, while the second plunger pushes it into the blister. And, again, a drawbridge-like arm presses the unit down and into position. With the blister fully loaded, it then advances to an elevator that extracts the loaded blister from the car, then slides it across and onto a conveyor belt. Here, the operator checks the contents, then loads the blister into a fold-over card before sliding it into a sealing machine. Heat and pressure from the sealer activates adhesive on the card. This seals the blister in between the 2 fold-over card pieces. For us, the benefits of automation have been significant. First, we can produce more product in less time. Before it took us on average 35 seconds to assemble 1 unit. Now we can do it in 7. That means we don't need as much inventory on hand, and we can effectively build on demand in response to big orders. Second, what once required a team of 8 people can now be done with 2, and with better quality. Third, our automated production facility requires half the space that our manual process required, so that's less fixed overhead for us. Finally, if we need to expand production in the future, and I certainly hope we do, we'll simply print out another production line, assemble it, and double our production capacity.
Advice for other small manufacturers?
Well, during the course of automating our business, it occurred to me that there must be thousands of other small manufacturers in the same position who'd like to automate but really don't know where to start. We accomplished what we needed with a very modest budget, and along the way we learned a whole lot. So I guess my suggestion would be to reach out to us because we probably can help you.